topic I wanted to cover in this class is privacy. And it's I guess an increasingly important area of when we talk about corporations and government having access to who you are and what you do. We're at a point now where data is being monetized, and data can be used against us by an adversary. And so it's really important to think about privacy in the context of yourself and how you use the internet. I'm going to first talk about website tracking. And to give you some context of where we're going in this particular class, I want you to think about you as a user, and we'll say this is our fictional user, Alice. There are people who might want to snoop on what Alice does over the internet. And so, for example, you might have the site itself might want to collect all of this information that Alice is sort of interacting with the site with, and then maybe sell that information to someone else. So that's one threat to Alice's privacy. Alice doesn't really know what this website is going to do with her data. You have the site might have relationships with an ad network. And so as part of browsing example.com, perhaps the advertisers for example.com might want to track Alice's behavior and use that for their own purposes. You also have people on the same network that Alice is on. So say someone is really interested in collecting information about Alice, maybe a parent monitoring their kid, which I used to do on my daughter, but now not so much. Or it could be maybe, and this is something I had a student looking at, was an intimate partner who's an abuser, right? So this would be a surveillance opportunity for someone to track and stalk maybe another person. You have people on Alice's device itself. And one of the things that surveillance software manufacturers will do is sell their software to people who want to collect detailed information on this target. And this happens in this domain of intimate partner violence, where, yeah, the spouse might actually plant something on the phone, or the intimate partner might do that on the phone to snoop on Alice. You have the ISP that Alice uses to connect to the internet. So maybe the ISP wants to monetize some access information from its customers. And so they're looking at this data. And then finally, you might have others in the network. So for example, an oppressive government wanting to monitor the traffic of all of its citizens to be able to respond to things that it might not approve of. So you have all of these different things that can go on. In this class, we're gonna first talk about website tracking. So we're gonna talk about websites collecting data on you, and then perhaps some of the third-party websites like ad networks that are also collecting this information about the users. And to do that, when we talk about tracking behavior on websites, we first need to talk about the mechanism that they're using to do this tracking. And so in order for me to talk about that, I'm going to briefly cover HTTP. I didn't really explicitly cover this protocol in the application security part because we have a whole course on web security, and there's enough in that course to talk about it. But I'm going to talk about a very specific thing in HTTP. And in order for me to talk about that, I'm just going to briefly talk about how HTTP works. So this is an application layer protocol for requesting and receiving HTTP HTML requests. And so this is the RFC that it was defined in 2068, consists of web clients or browsers sending requests to servers, and then servers sending responses. And so with this request, objects that you retrieve over HTTP, they're identified by a URL. The URL has the server name as the first part, and a path name on that server that this request is trying to access the content for. So basically a URI specifying the resource path of the request. And then the operation for a client is to do a DNS lookup for that server name to find the IP address of that server name and initiate a bidirectional TCP connection to the IP address on port 80. And it's port 80 if it's in clear text HTTP, and it's port 443 for the TLS protected version of HTTP or HTTPS. And then the server is going to accept this TCP connection from the client. And then the client, after getting a bidirectional TCP connection established, will send this request message to the server that includes the resource that the client is asking for, which is this path name. And this request is encoded completely in ASCII, in 7-bit ASCII. So this is what it looks like. This is the request part of HTTP. A web browser connects to the web server, sends the request, and the first thing in the request is this line, this ASCII line. This is called the request line, and it has the first part of the line is the method, like, do I want to get something or do I want to post something? So gets are retrievals of content, posts are submission of content. You can get the head of something, which says, give me the first couple of bytes of this thing that I'm looking for, followed by the URI path. So that's this part of the URI, followed by the version that you're using of HTTP. And then the client then sends some HTTP request headers. One of them, the only mandatory header in HTTP 1.1 is this host header. So this must be set when you say you're using HTTP 1.1, and it just says, well, what is the original host name that I am looking for this URI? Because multiple web servers can be running on a single IP address. And so that web server needs to figure out which one of those websites on my server are you looking for. And that's why the host header is mandatory. The other thing that gets collected are things about the client that the client wants to reveal to the server, like what web browser am I using? What languages do I want in return? There's some information about the client being revealed, which is why I wanted to show you these headers. Because yeah, you could say, oh, this is someone who speaks French using Mozilla 4.0, and that gives some information to the server. And whether or not that's information you want the server to have is another question that we'll address later. That's after the headers are sent, and you can have a whole bunch of these. I'm only, there's just 4 header requests, but you can have, if you look at a request, there's like a dozen, like sometimes even more that your web browser is sending to the server, and you can poke into the developer tools and see all of the headers that get sent. After this request is sent, you get a blank line carriage return line feed, and that ends the request. And then the server will parse this, see that the request is finished, and then process the request. And then the receiver, after parsing the request, will return an HTTP response message to deliver the actual content back to the client. And this is also encoded in ASCII text. And it consists, again, of the first line is the status line that says, this is the version I'm using. This is a status code indicating whether or not it succeeded, failed. If it failed, what was the failure? If it needs to be redirected, it'll be a different code. And so this is just giving you the result of the request, followed by HTTP response headers. And these are similar to the request headers, but they tell you information about the server itself and the results of the connection. So for example, this is the server software. This is the last time that content got modified. So this page.html was last modified in 1998. The length of the payload coming back, and then the content type that, hey, this is an HTML page. So you should, when the browser gets this in response, treat the content as HTML. Okay, and then finally, the actual data is sent back. Now, initially, HTTP was a stateless protocol, and it did not remember requests from a particular client between requests. It took a new request from a client, and it was like, oh, I'll just give you the data you asked for. Now, the fact that it initially didn't have any state was a problem, because if you want to do something like a shopping cart application, like Amazon, like you're shopping on Amazon and you're putting stuff in a shopping cart, the server needs to have a notion of a user session between itself in order to accumulate state that's associated with a particular client. And if HTTP is stateless, it has no way of tracking. And so the cookie mechanism was added to HTTP1 in order to allow a server to track the identity of a particular client. And almost every single website requires and needs cookies to be enabled in order to provide functionality to the user. So definitely social media, definitely e-commerce. This is an essential mechanism for HTTP. This is how it works. So Alice, again, is submitting an HTTP request to the server, has the request line, has some host headers. This is the first time Alice has visited this server. And the mechanism for cookies is for the server to say, you know what, I want to track Alice from request to request. And so I am going to use this HTTP cookie header that got added to the protocol. And the header name is the set cookie header. And I'm going to be able to store arbitrarily key value pairs on Alice's browser. And when and this data will get stored and maintained by Alice. And then the idea is that when Alice wants to revisit this server, Alice will supply these cookie values back to the server so that the server can understand that this is from a previous session. Okay, so that's the idea. That's the mechanism. And so when Alice then goes back to the server on a subsequent request, the HTTP request header is just cookie. And with this cookie header, the browser in Alice's web browser will actually set those cookie values based on what the server had set initially. And that's how this thing works. So this is the syntax of the set cookie header that the server is sending the client to store these cookie values. And typically, it's got set cookie with a particular value. And then there are sub-attributes. There are these attribute value pairs that you can attach to this cookie that specify the behavior of what this cookie value should follow. The first one is an expiration time. So if you only want this cookie to be valid for a particular period of time, say like on a bank site, you want it only to be valid for 15 minutes, then you'll say, you know what, this expires 15 minutes from now. And then the browser sees that. And if those 15 minutes have passed, the browser will delete that cookie, or it won't use that cookie when it revisits the bank again. Now, there are some cookies that have no expiration date. Like, for example, like if you visit a social media site, they want to track you forever. So they're going to send you a cookie that never gets deleted, right? So it depends on your application, and that's why they have this expiration time on the cookie value. You also can specify the scope of the cookie. So if you are a large site and you have a lot of subdomains, like Google has a lot of subdomains, and you want this master cookie to follow the user around on all these subdomains, you can specify that using this domain attribute. You say, hey, this particular cookie is good for all of these subdomains in my site. And it has to actually match for what the original, the top level domain is. Like your subdomains have to be within the original domain. So that's the idea. You could also say, you know, not only do I want to specify the subdomains, I want to specify the path within my web server to use this particular cookie. And that's what this scoping is. So this is sort of a coarser scope that talks about the site, and then the path is where within that site, which paths are valid for using this cookie. Again, this is giving the content server a lot of control over what state the client is using. The next two specify security concerns. For something like a bank, the bank never wants you to send your banking cookie unencrypted. And so you can say for my site, for wellsfargo.com, never send this cookie over HTTP, always use the secure HTTPS protocol when sending that cookie. And that's with this secure flag. The other thing that you can set is I want this cookie only to be used when I'm making an HTTP request. It turns out the JavaScript runtime on your browser allows you programmatic access to the cookies that are active on a particular page. And so if you don't want the JavaScript engine to have access to anything, any of your cookies, you can set this HTTP only. And then it's only the web browser that will access the cookie whenever there's an outgoing request that matches. You can't just collect that cookie programmatically using JavaScript's document.cookie variable. So that's another important security concern that you might want to set on a particular cookie. So the one field that is relevant to privacy, more relevant to privacy than any of these, is this new same site attribute value pair. And this just got put out a couple years ago. The same site attribute is a policy to control, specifies a policy to control how the cookie is sent when you are accessing sites. It restricts the use of the cookie over HTTP. So that's the thing that I want to talk about. And so just like, here's an example of a set cookie with a whole bunch, with a bunch of these attribute value pairs being set. And so for this particular cookie, this is a session ID. It's good for this domain, foo.com, for the top level directory. It's secure, meaning it only is used for HTTPS. It can't be accessed in JavaScript. And it's got this setting, same site strict. So what does this mean? In order for me to explain what same site does, I need to first talk about kinds of cookies. So the cookie that I talked about in the previous slides was known as a first-party cookie. So if you are on Amazon.com and you are trying to get stuff to and from Amazon, if your web browser is visiting Amazon, the cookie that Amazon sets in your browser and that you use subsequently on Amazon, that's considered a first-party cookie. You visited Amazon intentionally, and you are interacting with the site, and the cookie is going from you to Amazon. So that's first party. So you're on a.com and you send a.com. But within the Amazon site, if Amazon has embedded images that go off to some other domain, that's a third, and that other embedded image has a cookie that you have in your cookie store that gets sent when you retrieve that embedded image. That cookie is considered a third-party cookie because you went to Amazon and you used the Amazon cookie to retrieve a page, and then Amazon had a link, an embedded image link to foo.com, and then as a result of retrieving the embedded image, you send foo.com the foo.com cookie that you have in its site. That's called third party because you went to the first party, and then as a result, you're getting content from a third party. Okay, so this is a cross-site cookie where you're visiting a.com, and then as part of that, you're retrieving something from b.com with your b.com cookie. And your web browser has just been programmed to do this, right? By default. So here's an example. You're visiting a.com. You have cookies that are specifically for a.com. You exit A and you visit website B. And so website B might have an embedded image that is hosted by website A. And then as a result, you send the cookie that you had established as a first party interaction. Now you're using that cookie in a third party way to get access to website A. Okay, so this mechanism is what they're using to track you from site to site. This is how ad networks work. So cross-site tracking is really how an advertising network gets information about the products you're viewing, for example, or sometimes your searching habits, like what are you interested in? And they will, based on sharing these cookies, track you across, for example, what news sources do you typically go towards? Maybe if I know that you're either a Democrat or a Republican, or if you're religious conservative or you're atheist, I can actually track now and target advertising to you based on what I see your history is. So this is how money is made on the internet. So if you think about all the free stuff we're getting on the internet, it's coming at a cost of you being the product that that they're trying to monetize, right? And this has been highly successful. I'm like, it's neither good or bad. It's just kind of like the contract we made when we want to access free stuff. Okay, so this is an example of basically what's going on. You have this cookie, this tracking cookie. It's being sent across all of the different sites that you visit. And then the advertising cookie in green allows the advertiser to figure out, well, what is the data? What are the requests that this particular person is going through? And then this is where you can really get effective targeting of your ads. Okay, so how bad is this? You can, in your developer tools, you could go to a popular website that you visit quite often, and you can inspect the page. So right click inspect, and you can go and inside the browser, you can click on all the cookies that have been sort of set by this particular page that you're on. And you can expand out this cookie tab and you're like, oh, wow, I went to MSN.com and I definitely have an MSN cookie. So I should have that. That's logical. But then I have all of this other stuff. And you're like, huh, what is all this stuff? And what are they doing? And how can I find out what they're doing as a user? So you can find out what they're doing. There's a bunch of heuristic checkers that are going and looking at the behavior of these cookies. And they're trying to figure out, well, why are these cookies there? And so you can figure out, for example, what is this media.net company? Like, what is its business model? Like if I were a customer trying to do tracking, or if I was like a business trying to do the tracking, I would set up a relationship and say, well, what features do you provide? And that's what some of these checkers are doing. They're figuring out what is the business model for these sites that are embedding cookies on these pages, and then figuring out, well, this is what these cookies are probably doing on this particular page. And then you can go and you can look up, and this is a fun exercise. I don't think I might have you do this in one of your labs to just check for some of these pages just to see what they're doing. And then you'll get some different results based on the heuristic that you're using. I want to show you a demo of this because I think it's fun. Test a conservative news channel site, Fox News, with I think a more liberal one, which is MSN.com, and see which one tracks you more. And so there's this site, cookiescript.com, that I think is pretty cool. And so I'm going to just show you. I pre-ran these checks. So let me show you the site if I can bring it up. So this is cookiescript.com. So you basically say, this is basically a compliance checking tool. So one of the things that we'll talk about later is that these websites have to adhere to certain standards of privacy. And this is the EU has some strict requirements on the handling of personal data. And so one of the reason why CookieScript exists is that as a third party, it can validate your site based on all of these different privacy sort of laws that have been enacted. And so you can basically scan any site. You can scan your own if you have one. And so here's the scan for Fox News. And you see there are 32 cookies on this page in total, and then 7 of these are first party, and then 25 are third party, and then it'll categorize these things. And so you see a whole bunch of these things. 20 of them are for targeting ads. And you can scroll down and you can figure out which ones are. And so here are the targeting cookies. And so these are the different companies that are using the information being collected on you on Fox News. And so you can see who are the business partners of Fox News that are paying Fox News for this access in order for Fox News to then pay their content, like they have to pay their reporters, I would imagine. They have to pay for their website operation. And so they're using monetization collected from these targeting ads to fund their operation is the idea. Some of them are really clear. So that's definitely advertising, right? Advertising.com. And that's Yahoo's thing. So this is a pretty fun thing to do. Well, a sobering thing for some people to see how many third parties are in on tracking you. And then there are some of these are unclassified. They haven't gone through and taken a look. So that was what, 32. And then you can see for MSN is got a little less, 23 cookies, 13 are first party, and then 10 trackers. So you can go down here and see, these are the different tracking cookies and some Microsoft properties. So obviously there's a lot of Microsoft specific tracking going on in this particular one. They don't really share. Yeah, they keep it all in-house. They're not using these random third-party ones. This is all, well, like AppNexus is the only non-Microsoft tracking cookie on there. Whole bunch of Bing, yeah. And so that OSINT lab, Google shut down the profile collector part, I think, of that lab, and so now I'm using Bing. Bing wants the traffic, so it won't restrict our open source intelligence queries, at least not yet, because it needs to boost its numbers. Yeah, and so you see, I had to update that a couple days ago because someone was like, "Hey, Bing, the Google plugin doesn't work anymore," and I'm like, "All right, let me try Bing," and Bing worked. And so that's, if you're wondering, I'm not trying to choose sides here. I had Google, but then yeah, Google is on top of these kinds of techniques. The reason why these labs are breaking so often, like a Recon NG lab breaks, like I used to have it search LinkedIn, but then LinkedIn realized that people are scraping the profiles to target phishing attacks. And so they stopped allowing these brute force searches of profiles. And then I was like, okay, let me point that to Google, because you can say, okay, point it to Google and then restrict the site to be LinkedIn to try and scrape profiles. And now Google, or the people who are building that Google plugin, like basically had to shut that down as well. And so now I'm on Bing. So now that lab got updated to Bing, and it'll give you something, but it won't give you as much as it used to give you. And that's basically the evolution of these tools, because as soon as you see information being abused by an adversary, then the people who are being abused will protect themselves against that abuse. So that's just an interesting aside. Okay, so this leads us to same-site cookies. And this was something that was developed, I think, 3 years ago, and it was pushed out in a change on Chrome in 2020. And it was something that got implemented in Chrome and then updated in 2020. And basically, the way it works by default will kill the ad cookie. And that's basically a year after. So they pushed it out. They did a whole bunch of testing, and then they decided to make it the default. And this Apple and Google, who are the people doing the browsers mostly, and Mozilla. So Mozilla is doing the same thing with their web browser. The browser companies are like, yeah, these ad networks are really destroying confidence in the web. So in order to preserve the user experience, we're going to kill this cookie, this ad cookie. And of course, the people whose business model is exclusively on monetizing user data, like Twitter and Facebook, well, mostly Facebook, because that's their Twitter also is mostly advertising right now. They hate that, right? Because that's how they make money. So that basically wrecks their business model. So that was Apple and Google. Mozilla, Firefox, so Mozilla, the open source sort of backing for the Firefox browser, they have this total cookie protection. So this is better marketing than the same site cookie that we're talking about. They have this nice cartoon where, you know, before you had your cookies all in a pot that everyone could sort of access using cross-site accesses. And so the idea of cookie protection is like, you know, only Facebook can access Facebook cookies. Like only when you're on Facebook will you be able to get your Facebook cookies. Only when you're on Fuzzy Slippers will you be able to access Fuzzy Slippers. And this is in a picture, this is what same site cookies are. You only use the cookie for a particular site when you're actually on the site. So that's the idea. And so this had a huge impact on Facebook. And so this was earlier this year. They say as soon as this stuff gets pushed out, they told their investors that this is going to be a $10 billion hit a year. So this change basically wrecked Facebook's Meta's business model. And the reason why is because now the targeting of ads is a whole lot less effective. Now it's basically like the way we were doing broadcast TV ads, right? You have an untargeted ad that you buy on a broadcast television provider. It can't be personalized to the person viewing. I mean, it can be personalized a little in that, oh, the person who's watching this sports game is probably drinking beer kind of targeting, but not the kind of targeting that they're used to on the internet, where you could say, hey, you were just looking for fuzzy slippers. Here's an ad for fuzzy slippers. And then it's like, oh, that conversion rate's really good, right? And that was how Facebook was making just tons of money. Okay. And so now advertisers are fleeing the platform. They see the writing on the wall. Like if they're spending money on advertising, it's much more effective to spend it on a place like search engines, because on a search engine, you are explicitly looking for something. And so you should be expecting ad placements that are related to the terms that you are searching for. That ends up being the best way to do your advertising, as it turns out, once this has gone away. This was very effective when they had all that information about your profile. But now this is much less effective compared to just a straight up web search. And this is why, so Google is making tons of money on ads. This is why Google didn't mind doing the same site change, because it realized that, hey, I'm going to make ad money a different way now versus this one way that Facebook was basically relying upon. So that's the background story of this. And so they're like, so the day after, basically a $232 billion loss in valuation from Facebook as a result of this one change. So really interesting. And this is why now Meta, when you think about Meta, they're all about virtual reality and video ads. Now, that's the only other way that they can start replacing some of this revenue that's gone away from their business. So we'll see how well that works. Okay, so I'm going to talk about the mechanism itself now. And this is the same site cookie attribute, and the syntax is similar to other cookie attributes. And there are 3 values you can set in the same site attributes: strict, lax, or none. And so I want to talk about what this means. The idea of same site is that you are specifying whether or not the cookie can be used outside of its own site. And how it can be used if you're trying to use it. The site, the definition of what you call site is something that you publish ahead of time. And so there's a public suffix list that every content provider will submit. This is my same site policy, or these are the sites that are equivalent for my same site policy. And so, for example, you could have, say you're a company and you own web.dev, and you have subdomains in web.dev. You would like cookies to be shared across your properties. And so in this public suffix list, you'll say these 2 are the same site. If you are a place like github.io, which is hosting user pages per user, you're like, yeah, this user foo is not equivalent to this user bar. You shouldn't share cookies between those 2 sites. And this is why you have to define this suffix list, because these are logically and these are independent sites, independent content producers. This is the same content producer, and that's where the flexibility comes in when we talk about same site. Okay, so given that, there are these 3 settings. The first setting is strict, and this says you will only use that cookie when the domain in the URL bar matches the domain of the cookie. So I have to be on the site, navigating stuff within it for me to send that site's cookie back and forth. So this is the most sort of privacy preserving mode for the cookie. And this is typically used for banking sites. So if you go to the bankpal.com site and start navigating it, that's when the cookie is set. If you are getting an email from bankpal.com that has a link that links to bankpal.com, clicking on that will not send that cookie, because it's hosted, that link is hosted somewhere else. It's hosted in your email, in Gmail, or if some other website has a link to bankpal.com and you're on that site clicking, that cookie won't get set there either on the strict setting. You have to be on bankpal.com for the cookie to be set on requests to bankpal.com. If you have this strict setting and you click on a link that doesn't adhere to the strict policy, you can go to your developer tools and it'll say, hey, you know what? I'm not allowed to send you this cookie. So I'm gonna just warn you that this cookie didn't get sent. After you visit, so it's not gonna restrict your visit, you're gonna go to bankpal.com, and then subsequent requests on bankpal.com will send the cookie. It's just that initial request. Okay. Okay, so that's the difference. If you are on the website and you click on that link, it does include the cookie. Okay, the next one is same site lax. And this is the default in Chrome if you have not set the setting. And this is really what broke Facebook. So the idea of lax is that it's the exact same as strict, but you do allow cookies to be sent as long as you are clicking an A link, an actual, when you are in a link navigation thing, if you're clicking a link explicitly to bankpal.com, you're going to send it, even if it's hosted on a third-party site. Okay, so that's the idea. And that's the only difference between strict and lax, is that, so if you're on bankpal.com, both of these will send the cookie. But if you are clicking on a link that's hosted on a different site and you have the lax policy set, then clicking on that will send the cookie as well. The final one is none. And this is basically what we have right now. Anything goes on this cookie. Just send it whenever you are accessing that domain. So embedded images, for example, it gets sent. So any content that you're going for, as long as the domain matches, you allow cross-domain access, even on embedded requests. Okay, this is what it looks like in pictures. So for none, as long as this web browser is asking for content that's in green, it doesn't matter what page you're on, you send that cookie. Lax will send it as long as you're clicking a link, it will send it, and then eventually you will land on this page. So this is where it's kind of a first-party cookie as long as you are clicking on a link. And moreover, I didn't talk about this, that link can only be an HTTP GET. It has to be a safe request. You're only trying to access content or visit that site initially. And so sometimes bankpal.com is like, yeah, you know what? I'd like to have a personalized landing page. I don't want you to be able to do any banking from a link that's hosted off of my site, but maybe I don't mind that when you visit the page from another party that, you know, it's personalized, the landing page. So that's basically why this is only for HTTP GETs that the lax policy sends the cookie. And then finally, the strict cookie says, hey, only when you're on this page, clicking a link, will I send the green cookie. Otherwise, I won't send it. Other questions about the same site cookie and the 3 settings? So this is a pretty big deal when it comes to privacy of your behavior across the internet. And so now with this setting, you're being tracked less in this year than you were last year, I believe, at least. I don't have any data back that up actually. But I do believe with Facebook cratering their revenue, I'm like, okay, they were probably the #1 trackers on the internet. And if they're not making money anymore, I think I'm getting tracked less. That's my logical argument for that statement. There is this header. So this is an aside. This is a pretty meaningless header. The W3C wanted to support a header called the do not track header that clients could set to say, hey, content provider, I don't want you to keep any data and sell any data about me in my requests. And this is the DNT header. It is a request header. So this is Alice saying, oh, please don't track me. I'm going to set my DNT header to 1. And then the server is on the honor system, basically, to say, oh, DNT1, I'll not sell your data, but there's no enforcement of that. So this is why I put it out there. I don't think this has actually been very impactful, because without the enforcement mechanism, people just ignore it. There's no skin off of their back if they just ignore the thing and then sell the data anyway. Okay, so security has a history of measure followed by countermeasure. And so one of the things I want to talk about is like, can I track without using cookies? And that's what browser fingerprinting is about. So what is this? Almost quickly early on, there was these things called ever cookies or super cookies being developed, because people were realizing that cookies are being used to track them. And so they would do things like have basically a plugin that would delete their cookies all the time in order to prevent this thing. And so almost immediately, we had people who really cared about tracking develop alternate ways of tracking users that didn't involve cookies. And so you could do things like use HTML5 local storage, which is a mechanism for a website to be able to persistently store data on your laptop, which is very common now, because these rich web applications, they actually want to store content locally so that when you interact with their site, those assets are right there versus you going over the network. So you could actually store a cookie in there or cookie data in there. IP addresses. So you could basically track people, assuming that their IP address is stable. Their user agent, their language settings, other information like their screen size. Like if you could find a way of monitoring the browser or inferring the browser and the machine that the user is coming in from, you can identify that particular person from request to request. And that's the idea of these of browser fingerprinting. So let's talk about what they can do to track you. And so the question that we're going to ask is, well, what's in a GET request? Well, as it turns out, a whole bunch of stuff is in a GET request. So you have things like this. You have, what content is my browser able to accept? And you're like, oh, wow, this is a lot of information. What encodings can I accept? Can you compress that payload and send it to me? And which formats of compression do I support? What languages can I support? What is my do not track heading? And so on. So there's a lot of information there about the client. Another set of information that you might use is the user agent. So this has the browser, the version number, the operating system I'm using, the version of the renderer that I'm using on Mozilla 5.0. All of these things are sent along with the GET request. And so the idea of browser fingerprinting is that this request reveals so much identifying pieces of information about the machine that you're operating on, that a server can then just record that and say, this is a user number 1. It's got this kind of setting. So that's just the HTTP request. It turns out if you are able to run JavaScript on the client browser as it's visiting your page, JavaScript, the engine, allows you to do things like get the screen size, the screen resolution, because a lot of these websites will tailor their content based on the device you're on or the screen resolution of the device that you're on. So that's something you can do. The time zone you can collect that the browser has set. Any of the installed plugins, and moreover, the versions of those plugins you can collect from JavaScript. The system fonts that are on your machine. So if you installed a special font that nobody else has installed, that reveals you. So that's the idea of this browser fingerprinting thing. Okay, probably the most effective one is the link visited information, right? Like you have a browser history, and if you realize, like when you visited a link and you reload that page, it shows you that you have visited the page by graying out that link in typical HTML. With the JavaScript engine, like the tracker can send you a page with a whole bunch of links, and then your browser will color the visited links gray or a different color. The content provider can run JavaScript to get the colors of all the links that it had sent you in order to figure out which links you've already visited. So there's a way of getting your browser history without actually, by inferring the coloring of your styles on that link. And this is a runtime thing that happens with CSS. So here's an example of this. So I visited the MDN web docs and the YouTube site, and not these two pages. And because the CSS, so like an adversary is delivering you this page, and then within the CSS, as long as it's been visited, I'll say, hey, I want you to color this forest green. And then otherwise do the default, which is blue. And now I can collect, after I send you this page, I can collect whether or not you have visited certain pages. And I can use that to fingerprint you as a user. Okay, so this is pernicious, potentially. You could, at school, so at Portland State, you could be using a search engine to search for school stuff. And then later on, if you're like, oh, I'm at home and I have some query, some sensitive health query, I'm going to use that search engine to search for that again. And because the search engine has seen your browser fingerprinting from the previous one, they can associate you with this particular one. So how bad is this? Give me measurements. So there is this EFF Panoptic study where they only used 8 attributes. So I showed you way more than 8. They were like, well, let's just use 8 and see how effective each one of these attributes is in uniquely identifying the person visiting. And so it turns out they used almost 500,000 users, and 83.6% of them had a unique browser fingerprint across these attributes that they were using. And so here's an example. They used user agents, they used accept headers, they used whether or not cookies were enabled, they used the screen resolution, and they used the time zone were parts of these things. And then they were like, well, which ones of these are the most effective at identifying this particular person? And they looked at this, and what is the entropy that you get when you use particular variables? And of course, the user agent the user agent, the plugins, and the fonts. These are just using these 3 gets you a huge amount of information about the user that's visiting. And of course, the one that is the least effective is cookies enabled, because everybody enables cookies, right? So that was the least effective of all of them. So this is kind of scary, right? And so the next thing I want to talk about are, well, what are some laws here? This is kind of like the Wild West. And what should be allowed and what shouldn't be allowed. And one of the things that they have developed are laws to basically, if I have this information about who you are, what am I allowed to do in terms of selling your data to other people? And so this is something that's very much recent developments, is what do we do about this? What can sites sell on you? Because they are going to get that information from you regardless. And this is governed in 3 ways. The first way is federal or national law. Now, or international, well, I guess I call this federal. So the only federal law that's out there right now is in the EU, and this is the GDPR. This is a privacy act that got enacted. And part of this is the right to be forgotten. And so one of the key aspects of GDPR, not only does it restrict the amount of information sharing that sites can sort of sell about you, you can, as a consumer, say, forget all of my data. And they are mandated to be able they are required to delete your data as part of this GDPR law. In the United States, we do not have a federal law. And we are working on a federal law. There isn't enough political, I guess, energy to do a national privacy law. But there are particular states who really care about this, who are enacting their own laws in the state. So California, as they are wont to do, will act first. So they have a privacy law that's similar to the GDPR, but not as restrictive, because realize that California houses a lot of people making money by monetizing your data. Colorado has one, and then Utah has one as well. And so this is basically how it's being done right now. And I think as soon as we have enough different state laws in place, I think there might be the ability to create a federal law around your data. What we have now is because websites realize that people are paying attention to the privacy, we have privacy policies that sites will publish. And hopefully that will validate to their customers that they care about privacy. It's kind of like companies saying, we really care about security. It's like, it's kind of like marketing. That is what a privacy policy is for a site. And so this is basically self-governance of the site. But even though it's self-governed, if you say you're not going to do something in the policy and you don't do that, then this is an FCC issue. This is basically how it's governed. And so they are upfront as to whether or not they're going to sell your data. But if they tell you they're not, and they do, then they can get basically policed out of it. And so these policies are described within terms of service. And so again, who reads a site's terms of service? It turns out nobody does, except for this particular site. And this site, terms of service, didn't read. This came out of the B-Sides. I don't know if any of you were at B-Sides. I went to that talk and I'm like, oh, this is brilliant. This is a site that basically tries to read all of the terms of service that the company provides and then boil it down into an executive summary. This is what, and moreover, an executive summary that points out things that you might not want that site to do. And then it gives a rating as to what it believes this privacy policy, how effective this privacy policy is. So here's YouTube's, and they don't do so well because they can view your browser history. When you delete a video, it's not really deleted. They're using third parties, cookies. So this is something that I don't know how up to date this thing is, but you can go to the TOSDR site and then look up how they judge a particular site's privacy policy. So that's an interesting site for you to look at. Here's Apple's. So Apple also, I mean, this is kind of a harsh grader. This site also fails, almost fails Apple. And then the reasons are given. And these are things that you know, like if you read the terms of service with a fine-tooth comb, these would be the things that you're like, oh, that's not good. And that's when they boil it down to 5. And then here is one, DuckDuckGo. This is a search engine that doesn't keep any of your searches or your data, the data on your searches. So they advertise on the radio a lot, so you might have heard of them. And so if you don't want the thing to be tracking you, like, you know, when you do Google searches that, you know, have your Google cookie with it, yeah, they can aggregate your searches and see the history of your searches. DuckDuckGo won't do that. So and then if you look at these policies, and it is only looking at the policy, what they're doing on the back end, they don't know. They're just looking at this privacy policy. Okay, so with these policies in place, one of the things that was also described in this B-Sides talk was a service called Delete Your Data. So if you, as a result of the GDPR, all of these sites that are collecting your data must have a facility to delete your data, otherwise they can't operate in the EU. And so this delete your data site was like, you know what? We are going to try and make it easy for a user to delete their data across all of these sites. Now, the problem is that this is a manual process because every site has their own way of requesting you to be forgotten, for you to have your data deleted. And so this was a single site that says, hey, delete my data across all of these sites, and they would do that legwork for you. So it's very convenient. It's like a delete your, like a GDPR aggregation, a right to be forgotten aggregator, where you can just in one step be forgotten across a whole bunch of sites. And this is their architecture. I copied their architecture from the slide that I found from them, and then they built this entire system to delete someone's data automatically. Okay, so this is an emerging battleground, and it's probably going to need to be regulated soon because there are companies that are basically assuming that you're not going to read the terms of service or that you don't care, taking your data and selling it in ways that probably aren't of societal benefit. So this particular company was tracking, user behavior across these, sensitive areas, and then selling it. And they're not vetting who the purchasers of that data are doing with that data. So this eventually is gonna lead to regulation. Okay, I'm gonna talk about protecting privacy and anonymity next. So to start with, I need to get my clicker back. Suppose we do all these protections from before. We delete our data, we disable cookies, we disable JavaScript, we use a new incognito window or private browsing for every site that we visit. The question is this enough to preserve our privacy? And I'm going to go back and take you to this figure again. We have focused mostly on the website tracking, but we haven't really talked about what happens if the adversary is in the network monitoring everything that you do, seeing all the different sites that you visit, and tracking you just based on your network traffic. And so the goal would be, hey, I want to actually protect not only the secrecy of my communications, but I want to be able to protect the privacy of them in terms of the endpoint locations of the communications that I am sending to and from the network. And the idea of this is that I want to be anonymous in the network. And so this is the exact opposite of authenticity, right? Authenticity, I'm trying to validate your identity. Anonymity, I'm trying to make it so that nobody can identify me. And so these are, you can think of these things as polar opposites. And so there are many reasons why you would want this. So whistleblowers often don't want to be located so that they, so that they're not, so that people don't go after them. And then in general, you don't want to be tracked over your network connections. We saw this initially with Oblivious DNS. If you remember Oblivious DNS, we had the resolver, we had an ODNS resolver and an ODNS sort of stub. And this prevented the person in the middle from knowing either the sender or the request or the receiver and the request. So this was the idea of Oblivious DNS, was to use these encryption layers to protect parts of the information in each step of the DNS lookup. And that prevents any particular node from getting the full information about the client and the request and the destination. Tor, as we're going to see, does exactly the same thing. It's basically very similar to the way Oblivious DNS works. Before I talk about these systems, though, I want to talk first about the idea of crowds and K-anonymity. And this is one approach. K-anonymity is one approach for obtaining a degree of anonymity. And moreover, it is an approach that allows you to quantify what level of anonymity am I going to achieve? Because it does matter. Anonymity isn't one of these things that you either have it or you don't. It's basically a degree of anonymity that you can get. And the idea of k-anonymity is that you're going to leverage the power of crowds to hide. When you go into a crowd and then your access comes from the crowd, then it's hard for that person to identify who you are. This is why in like hacking movies, they're like, oh, I'm going to go to a cafe and do the the lookup. Which movie? I'm watching so I don't know if you know the Bourne Identity movies, but when he's doing all of his lookups, he's going to a cafe and he's doing these lookups. And so that's the reason why, because then you hide in the crowd of people using that open access point. And so that's the idea of k-anonymity. This term was actually coined by these two computer scientists, and the term that they used is defined this way. When you release data, it has this k-anonymity property if the information for each person can't be distinguished from at least k-1 individuals. That means you can't zero in more than just a group of k people given this data release. So here's a question to think about. What percentage of the US population can be uniquely identified via date of birth, gender, and postal code? So think about that in your head, and I'll give you the statistic. This is 87%. Yeah, I came across this and we well, this is also from 20 years ago, but I can't imagine this. There's nothing in the last 20 years that would have changed this. So if you are in a particular postal code and I know your date of birth and gender, yeah, 87% of the time, you are the only person in that postal code with that gender and date of birth. Think about adding just one or two more attributes. And then you realize that, yeah, some of the personal data you put up there, yeah, that even if you took your name out, you would still be identifiable. And this is one of the issues with, hey, like for medical research studies, oh, I'm just going to anonymize the name and the address and just say, you know what, that's anonymized. Like this data is anonymized, I'm going to share it because I did my due diligence, but then they don't realize how, what is the k-anonymity property of the data that I am releasing? And as it turns out, if there are enough other attributes there that are public knowledge or that are known, you might as well not have anonymized the thing. So that's just something to think about. So the example I'm going to use for k-anonymity in practice is something we've actually talked about before. This has been applied to looking up whether or not a password has been leaked or not. So have I been owned? We talked about that earlier. It basically aggregates 4 billion, no, not 4, 2 billion, I think is the number right now, 2 billion compromised usernames and passwords. And they were like, you know what, it would be really useful if people are able to look up whether or not a password that they're going to use has been breached. Okay, so that actually is this password checkup feature. There are some plugins that allow you to go, like password managers can basically say, hey, these credentials have been leaked, or this particular password has been, leaked in a data breach. And then that allows you to say, change your password kind of thing. So the way this service initially was going to work was that, okay, well, you have a password you want to check. Why don't you hash it in all the different sort of ways passwords can be hashed, and just send me the hashes. And I'll check the database. And then after I check the database, I'll let you know whether or not it's been breached. Are there any issues with that? Like why is that a bad approach? What might be a drawback of doing that? The question is do you trust have I been owned? And even if you trust have I been owned, what about hashes that haven't been breached? Like, can someone see those and then use those to crack new hashes? Like, and so if I set up another site that looks like have I been owned, can I start collecting hashes? That can happen. That's the credential harvesting attack. So this is the notion is like, oh, just send me your credit card number and I'll tell you if a hacker has it. It's the same problem. And you're like, okay, I actually don't want to send you that, but I actually want to know whether it's been breached or not. So how did they solve that problem? So they solved it. Well, the other approach for solving this problem is say, you know what? I don't trust have I been owned. Hey, have I been owned? Just send me the entire breach database and I'll just check myself. So that's a problem also, because have I been owned? The reason why they don't want to publish that data is because adversaries could use the 2 billion. Like you're basically like, oh, sweet, have I been owned? You're basically doing all the hard work for me. I am not going to have to like purchase a bunch of breach data anymore. I'll just download it from you. And so you also don't want to give up the entire database. So it's bad for performance because it's 2 billion password hashes is pretty big, and it's bad for security. And so the idea, what they did to implement this service was to use k-anonymity. And so the idea of this, what they built was to truncate the hash based on the number k that they wanted to be anonymous across. So you're going to say, hey, I have this password hash. I'm not going to give you the complete hash, and I don't want the entire database, but I'm going to give you this hash that has the first n bits truncated. And I'm only give you part of it. And then you give me all the hashes in your database that match that part. And that's going to give you k hashes, approximately k hashes. And then I'm going to ship you those k hashes. The have I been owned is going to ship you that, and then you're going to look it up. And so you don't have the entire database. Have I been owned doesn't have your actual hash. And then that's how you get this thing to work. This is what it looks like. So you have a browser plugin that's monitoring the passwords that users are trying to set on the site. And you say, oh, I'm going to say Hunter2 is a very famous password. So I'm going to say, I want my password to be Hunter2. And then this JavaScript is going to do a bunch of digest hashing. And it says, well, here is the digest hash of Hunter2. Has it been breached? And then the browser, as part of this plugin, says, you know what, I'm not going to give you the entire digest. I am going to give you the first 4 sort of hex digits of the hash. And then the have I been owned service is going to say, I'm going to go into my database and give you all of the hashes that begin with that prefix. And then, of course, this very first one is the one that matches. And then you're going to say, okay, I've been part of a breach. And in this way, you get the best of both worlds. You get to figure out whether you're there, but you don't have the fact that you don't allow people to have the full database, and you don't have the have I been owned site have the actual the hash that you're looking up. Okay, so that's just an interesting idea. This is another application for k-anonymity that is a not so good application of it. So again, k-anonymity is either good or bad based on what you do with it. And so here's one where it's been used to launder cryptocurrency. So who is it? Charlie Munger, the guy who's doing Berkshire Hathaway, is like, this is like the cyber criminal's dream was cryptocurrency, because they could basically have a business model that goes beyond law enforcement. And so one of the key pieces of cryptocurrency is the ability to launder the money, which is to leave, like the ability to take that the ill-gotten funds and to be able to massage it in a way that you can then produce currency that can be used without tracing. And so what happens is in cryptocurrencies, there's a ledger for all of the Bitcoin, for example, that has been transacted. And if you are so say the government pays out a whole bunch of Bitcoin to a ransomware, or maybe a school. Say a state government or a school who has been ransomware pays the adversary in Bitcoin. The problem that the adversary has is that Bitcoin is going to be tracked from now on. Like every single transaction with those particular coins will be monitored by the FBI. And so as the adversary, you're like, I want a way of generating fresh Bitcoins that can't be traced back to this original ill-gotten ransomware payment. And so the idea of a tumbler or a mixer in cryptocurrency exchanges is to have a clearinghouse account that will basically mix all the coin transactions so that you can support k-anonymity. And so I'm going to start with a 3 anonymity example of this. And so the idea is you have some kind of account that is the mixer, and then this account will get user deposits. And this could be the tracked Bitcoin. It will take all of these Bitcoins into its mixer and then issue coins to other wallets after it's done this mixing. And as a result, because this mixing has happened, any subsequent transaction for each of these 3 coins, these goes to 3 different wallets, has the property of being free anonymous. It could only have been one of these 3 wallets, but you can't figure out which one. Okay, so that's basically what a mixer is. And so the question is a figure of a mixer, should this be legal? Right? You have a bunch of Bitcoins from ill-gotten transactions. You have this one account basically doing all the mixing, taking a cut off of the mixing, and then redistributing the Bitcoins. So this is basically the clearinghouse account. Okay, so it turns out this is not legal. And so this is an example where this is the Helix Bitcoin mixer. They finally tracked this person down, and then it's basically he's facing 20 years in prison. But here's another example that's more interesting. An open source smart contract deployed on the blockchain that can do the mixing programmatically. No one owns the smart contract. It is just sitting there mixing Bitcoin, mixing Ethereum in this case, programmatically. Who can you arrest? You can't arrest a smart contract. You can't really arrest the writer of the smart contract unless you, I mean, I don't think you can unless you can prove that the intent was to enable criminal activity. And that's hard to do. Like if you create a mixing contract, like I create a mixing contract as part of an academic exercise and release it. And if somebody is using that, well, that wasn't my, using it for criminal activity. Well, that wasn't my original intent. I was just implementing K-anonymity, right? And so this is basically how the North Koreans are monetizing this was their procedure for laundering any of the cryptocurrency funds that they were getting. And that's basically how their economy runs right now, is via cryptocurrency. That's how they get that capital injection from, because they're heavily sanctioned as a country. This is the way they generate money, you know, getting Bitcoin payments and Ethereum payments, and then laundering it. And this was one of the, Tornado Cash was one of the, they were one of the biggest users of Tornado Cash. So then what can you do? So as it turns out now, the way they have to do it is they have to basically sanction every single address that interacts with that smart contract. So now they're labeling every transaction as something that violates the law, is effectively how they would do it. And so this is an interesting thing, because if you have implemented K-anonymity in a way that can't be shut down or broken, then you would have to just say, I'm labeling the entire crowd as a problem, as criminal, and then that shuts the whole thing down. So that's just an interesting aside. Okay, so I talked about Tor and how Tor enables network anonymity. What does Tor do? The idea of Tor is to hide the identity of the endpoints, basically their IP addresses, using crowds and using encryption so that the request itself is also confidential. So not only is your location confidential, but the content is as well. And so there are 3 goals for Tor. It's sender anonymity, receiver anonymity, and then the unobservability in terms of not being able to see who's using the system. Okay, so many applications of Tor, avoiding censorship, avoiding surveillance. Law enforcement often does this to hide the fact that they are probing particular people. So they don't want to be, you know, you don't want to let the sort of the target know that you're trying to figure out what they're doing. So these are approaches. This is the stick figure explanation for what Tor does, and it's based on onion routing. So the idea is that you have users and you have a network of Tor nodes. And then this is well known, these routers. And each of these routers has a public key, or you could say has a public key that you can use to encrypt traffic to and from each of these routers. And then eventually you want to go to this destination. And so the user has an unencrypted request to go to this destination, but they don't want the destination to know the location of where this is coming from. And so what they do is that you have these keys. The user is going to send up and create an encrypted payload. It's going to encrypt the request in the purple key, and then encrypt the purple stuff into the with the green key, and encrypt the green payload with the yellow key, and then send that whole payload to the very first hop, which is the yellow key hop. The yellow key is going to, this is like the Russian doll analogy. It's going to decrypt the outer Russian doll and then send the green Russian doll in the interior to the onion router. And then the green router will pull out the purple doll, send it to the final, the exit relay. And then finally, the purple node will decrypt the purple payload, and then you get the unencrypted request. And now this destination doesn't know the identity of the user. It basically is looking at this and saying it could have come from any one of these nodes in this onion router. And actually, I would have to attack one of these onion routers to actually figure out where this original request came from. So in that sense, the sender is anonymous. It's hard for the receiver to know where this came from.
So there's no metadata, no request identified at all.
So then the destination is going to have to do like browser fingerprinting or that kind of stuff in order to figure out the identity of the user. So yeah, so you still are allowed to do the application layer browser fingerprinting stuff, but this hides the IP address. So without this, the destination knows not only the browser fingerprint, but the IP address of the sender. So if you recall, the IP address could be used as your fingerprint. This is just focusing on that part being anonymous, just erasing that. Okay. So this is how it works. Alice picks a random path through the Tor network. And so she has a collection of these nodes. And let's say she picks N1, N2, N3, all the way up to N sub N. And it's like, I'm going to use this circuit to send a packet to example.com. She sends this onion, and this is done with all those layers I mentioned earlier. I'm going to say this is the exit node, N sub N. And I'm like, here, I need to do the inner part of the onion. So using the key for N sub N, I'm going to encrypt my original message in plain text. And I'm going to say the location of where this encrypted message should go to is the actual node ID. And then I'm going to backwards construct this onion based on the path backwards through the network. And then I'm going to send this onion into the very first node of the network. And so this is where this payload is sent. So this is what Alice will send to N1. It's got the key of N1. So this is the encrypted key. And then it's saying when N1 decrypts this payload, the result of that decryption should go to N2. And then the encrypted payload is encrypted with N2's key. And this is because she has collected all of the keys for all these nodes inside of the network. Okay. So node 1 is going to decrypt that outer piece, reveal the inner piece that says send the next part of the onion to N2, and then send N2 this part of the inner doll. And then N2 is going to get that and is going to do the same. And so it goes to N3, and then N3 gets this payload and then decrypts that, and then so on, all the way to N sub N. And then you get that plain text data. Yeah.
That circuit entirely ahead of time?
Yeah, so Alice has to create that circuit ahead of time. And moreover, if she wants to decouple requests to example.com, she would have to create a new circuit for the next request.
And none of that, there's no residual evidence of the path along the way?
Yeah, there's no residual, because all the state is kept with Alice.
Okay.
The Tor node is just blindly, more or less blindly decrypting and forwarding. Yeah. So you can see, so it's pretty obvious. You're like, oh yeah, that's gonna hide Alice pretty good. And Alice does have control over the path that is taken through Tor. And this will happen in your lab, I believe. I'm gonna have you, so you're gonna set up this in your browser, and then you're actually set up another node, not a Tor relay, but a backend node, you're going to see that your IP address, I'm going to have you use Tor, visit this what is my IP address thing, and you're going to see that sometimes it shifts, right? Because you don't want that what is my IP address to know that this is the same browser hitting it. And so you will get these different IP addresses because you're going to select what these are, different exit nodes is what these are called. And so then.
But what I don't understand is like the original payload that gets packed inside like the onion. It's like when you're sending it out to the Tor network, you're scrubbing it or what?
It's encrypted using only this person can decrypt the original payload. Because again, if you remember.
Oh, and then, okay. And
Yeah.
then, like N sub N would then send the payload as if it was the original requester
Yeah.
to the.
Yeah.
Got it, okay.
Yep.
What about responses from the server?
Yeah.
You would have to have the server do the opposite. Yeah.
That it knows how to come back.
Yeah. So it would respond. Well, this is the key. This person would have to also. This is a special. The exit node and this is called an exit node, and the guard. They would have to actually work on the response. Yeah. But that's hidden. Like I'm not going to actually cover this. Yeah. But you would have to actually do that piece as well. The return path. I figured just one explaining it the one direction was enough. But yeah, you're right. You're exactly right. You have to actually have the return path as well established. Yeah. Okay, so the entry node is key. This is the only place where you have the identification of the original person. And so that's key with that. And then the exit node also knows the final destination, but and the actual payload. But there is no node that has all of the pieces. This is very similar to Oblivious DNS. There is no node that says this person, Alice, sent this particular request to this particular destination. The exit node has the request and the destination, but doesn't have Alice. And so N1 has Alice, but doesn't have the data or the destination. And this is how you can split the thing up. Okay, and then the relays are just doing dumb things. So this is how it works. You download a bunch of relays from a directory server, which is semi-centralized. And this is a single point of failure unless you do something else, which Tor does something else because it doesn't want to be brought down. You select a set of relays to establish a circuit, and then you basically send these requests through the circuits that you have established through Tor. And then in order to prevent people from tracking all of your activity, if you're using the same exit node every single time, they might track you. And so you're going to eventually periodically shift your relays, your exit circuits, so you can use some other parts of this. And this results in this nice figure where, yeah, the things in red are unencrypted, but because you're using all of these relays, you can't really trace. And this is the K anonymity part of this, where you can't really trace that this request A actually started all the way over here with Alice in this case. Okay. So this is hugely popular, 2 million daily users, 6,000 relays, 100 gigabits per second of aggregate traffic. And this is basically, so all of this is just talking about sender anonymity. The other thing that you might like, if you see in this model, the destination, the location of the destination is known. The other part of Tor is what happens if I want to implement receiver anonymity. And so in the previous example, the sender is assumed to know where the recipient is located. But the idea of providing anonymity to the recipient, this underpins what they call the dark web or hidden services. And more often than not, hidden services are for ill-gotten sort of criminal activity, but there are hidden services that are legitimate. So for example, these news organizations that want to accept content from sort of whistleblowers, they might want to create an onion service so that the destination isn't revealed to people monitoring the client. So say say all of the requests going to, well, it works with sender anonymity as well, but sometimes the receiver also wants to be anonymous. And so the idea of hidden services is to protect both endpoints. So you're going to protect the client using the sender anonymity that we talked about before. But if you don't want the client to know the destination of the request, then you can use this hidden services part of Tor. And so the idea of hidden services is that you have some kind of onion service directory, which is a rendezvous. It's a level of indirection that allows the client and the onion service to rendezvous somewhere in the Tor network. And by doing so, the client doesn't know the destination of the service, and the service doesn't know the destination of the client. Now, to begin with, the onion service has to have some named attribute that labels their service. And so you'll see that some kind of hash.onion is typically what the onion service will establish. And that name is chosen. And then what happens is the onion service running on this particular name is going to choose and publish an introduction point in the Tor network. And this is going to be used for the client to connect up to figure out a rendezvous point in the Tor network. So that's what happens first. The client is going to then learn what the onion address, so this name name identifier. This isn't an IP address at all. This is just some kind of random name. This random name is going to be put into this onion service directory. And then the client is going to learn that out of band somewhere. And then what happens is that the client is going to look up the introduction point for this onion service that the onion service basically establishes in this service directory. And so by establishing this introduction point and by setting its entry in this onion service directory, now you have a level of indirection so that the client looking for this service can look up the introduction point in the service directory and then connect up to this service directory. Now, before the client connects to this introduction point, the client is going to say, I am going to establish a rendezvous point somewhere in the Tor network for me to communicate to this onion service with. And that's the next piece of this. And then I'm going to establish a connection to the introduction point and send to the onion service this rendezvous point in this introduction point. So that's how this works. Rendezvous point goes to the onion service, and then this rendezvous point will then, the onion service will then connect up through the rendezvous point. And this is the thing that's going to mediate the communication between these two things. And so in this way, the client doesn't know the final destination of the onion service, and the onion service doesn't know the destination of the client. So you get anonymity on both ends of this thing. Okay, other questions about hidden services? You will be setting up a hidden service in your lab. And that's why I wanted to show you this, because you're basically going to bring up a compute engine virtual machine. You're going to set up Nginx to be the onion service, and then you're going to run the Tor thing to make it a hidden service. And then you're going to see, well, if you connect up to the IP address directly, you'll see that you'll get the particular piece of content. But then if you use Tor on that onion name, you'll see that you won't get that address. It'll be hidden. So that's the lab that I'm having you do. Hopefully it still works. So many things have broken in this last week that I'm like, knock on wood. Let me know if you've run this thing and it doesn't work. I'll try and fix it quick. Okay. Okay. Let's see, 4 minutes. I'm going to briefly talk about attacks on Tor really fast to wrap up. There are attackers are going to want to bring Tor down. And so there are different threat models that Tor is attempting to prevent. One is that the attacker might run the relay, right? And this has happened. Another threat is that the destination might be malicious. And finally, another threat is that you could have an adversary observing a lot of the parts of your network, and you have to have ways of protecting against this. And the threat model that Tor is protecting against is a non-global adversary. Right up front, they're like, if you have an adversary that owns all of the different networks and can monitor all of them, we aren't very secure against that. And so, but if you have just a local adversary, we should be able to protect against that. So that's the idea of Tor. One of the attacks on Tor is a malicious ISP can block all of the access points. They can just download all of the Tor nodes and say, I'm going to filter all the traffic to all those Tor nodes. So that's one attack. The countermeasure that Tor has deployed is to provide a set of entry points that are secret, or to only allow nodes from certain areas of the globe to get a subset of the Tor relays, to never let a single requester get all of the nodes in the network. That's another way of doing this, or providing some out of band way of advertising networks as well. And so this is what happens. You can have private Tor bridges that are released via email, phone, or some out-of-band channel is the idea here. You have another attack where what happens, even if I don't have an IP address filter, what happens if I can just see the negotiation to the guard? And it'll look for that traffic and then immediately shut that down. Because in the end, all traffic has a fingerprint. And if I can fingerprint that initial transaction to a node, I can basically filter that. And so the countermeasure to this is steganographic approaches for hiding Tor traffic. So this is where these proxies come in. So obfuscating proxy, I like this one, Stegosaurus, because steganography, and then Tor, and then this is the dinosaur. So I kind of like that. And then format transforming encryption to make the Tor payload look like a regular web request, so that it's hard for it to determine that this is actually a Tor thing going on. The other one that's really hard to protect against when you're talking about nation states is a correlation attack. And so the idea is that if you do have a global picture, then you can correlate traffic coming into the network on entry nodes with traffic that is exiting and their destination. And in this way, you can, in fact, identify the source of particular requests. And this is what was reported last year. Someone is running about 1,000 of these relays in order to do this. And if you happen to have picked nodes that are all part of the relay, you lost your K anonymity, because now it's just they have both ends and they can actually detect your traffic on both sides. Okay, so that's an attack. Okay, so that's all I'm going to talk about. There are other attacks on Tor. This is an emerging battleground. I am going to end here, and I guess yeah, see you all next week for the final. And yeah, hope you had a good class.